Hello, today we're continuing with our series on electromagnetic radiation, looking at the Poynting vector. This series has videos on what is light, the Poynting vector, Fresnel equations, polarization, the interaction of electromagnetic waves on metals and waveguides. The Poynting vector is a measure of intensity of electromagnetic radiation. Electric and magnetic fields have energy. Electromagnetic radiation has electric and magnetic fields, and therefore it has energy. Sunlight can warm you if you lay out in it. Indeed, if you lay out in it too long, it can burn you. That's because there's energy. And the heat that gets from you, or from the sun to you, doesn't get there by conduction or convection. It travels over 93 million miles of space by radiation. So how is energy contained in electric and magnetic fields? Well, let's think about an electric field first of all, and we'll start off by considering a capacitor. Capacitors are typically parallel plates of area A, or more accurately overlapping area A, a distance d between the plates, and what we do is we put a potential difference between the plates. The potential difference is V, and what will happen is that in the way that this is designed, there will be a negative charge on this plate here, and that will induce a positive charge on the plate below, and because of that there will be an electric field between the two plates. From our video on capacitors, we established that the definition of capacitance was the amount of charge per volt. So it's the amount of charge on the capacitor determined by the voltage that is applied. We also learned that the capacitance was proportional to the area of the plate divided by the distance between the two plates, and the constant of proportionality was epsilon naught, which is the permittivity of free space. We also learned that the energy stored in the capacitor, that is of course stored in the electric field, is 1/2 CV squared. And we know that the electric field, that's this field here, between the two plates, is equal to the voltage divided by the distance. It is measured in volts per meter. So let's take this formula here and apply what we already know. We now know therefore that the energy stored in a capacitor is 1/2 times C, which is epsilon naught A over D, epsilon naught A over D, times V squared. Well, V is E times D, so that will be E squared D squared. And you'll notice that one of the d's cancels, and that's equal to 1/2 epsilon 0 E squared times AD. And AD is the volume of the capacitor. It's the area times the distance. That gives you a volume term. So now we can create a new concept, which is energy per unit volume. So energy per unit volume, which we'll call UE. So this is the electric energy per unit volume, the electric field. That's going to be 1/2 epsilon naught, E, not A, E squared. And that will be measured in joules, which is the measure of energy, per meter cubed, which is the measure of volume. So this is the energy contained or stored in an electric field in a capacitor. Now let's move on to think about the energy stored in a magnetic field, and for that we're going to consider a solenoid or an inductor. We wrap a coil of wire around some kind of maybe iron bar. The cross-sectional area is A, the length is L, there will be a current flowing in the wire, I, and we know that that current will generate a magnetic field within the inductor, inside the inductor, of B. This will be a hollow, I mean it doesn't have to be an iron bar, it can be typically a dielectric, but there will be something around which you can wrap the wire, but it will be hollow in the middle, and in the middle there will be a magnetic field. We'll also say that there are N turns of wire around the solenoid. The current flowing creates the magnetic field in the centre of the solenoid. Now, from the video on reactance, resistance, reactance and inductance, we learnt that the magnetic flux is equal to the value of the inductor times the current that is flowing. From the videos on electromagnetic induction, we know that flux is equal to B, the magnetic field, times A, the area, times N, the number of turns in of the wire. And we also know that the magnetic field is equal to mu naught, which is the permeability of free space, times N over L, which is the number of turns per unit length, times the current, I, and that gives you, if you just rearrange that formula, that the current is equal to BL divided by mu naught N. We shall need that. So, using these formulae that we've got here, we can now do a little bit of rearranging. Let's take, for example, the top one. Phi, the magnetic flux, is equal to the inductance times the current. The EMF is, of course, d phi by dt. And if we take d phi by dt, well, L is the inductance, that's a constant, so that is going to become L, but now it's the rate of change of current with time, because you need a changing current here, and then you get a changing EMF. And then we say that power is voltage times current. Well, that will be, the voltage of course is the EMF, same thing, L di by dt times the current, I. And now we can simply create an integral by taking the dt up here. We get that the integral of power dt is equal to the integral of L I dt, sorry, Li di, the di term is here, and if we do the integral we will find that of course power times time, well that's just energy, so that's the energy in the magnetic field is the integral of Li dt, which is of course a half Li squared. So that's the energy stored in the magnetic field which is associated with the solenoid or inductor. Now we recall that the magnetic flux, we've already stated this, is BAN, the magnetic field times the area, cross-sectional area of the solenoid, times the number of turns of the wire through which the current is flowing. And since B is mu naught N I over L, that is B, we've shown that previously, times AN. Phi is mu naught N I over L times AN. So since you've got an N times N term, that actually becomes mu 0 mu naught N squared IA divided by L. But we also know that phi is equal to Li. The i's cancel, and now you've got that the inductance is equal to mu 0 N squared A over L. And now we can say that the energy stored in the inductor is what we discovered just a moment ago, a half Li squared. So let's now just substitute in for that. Half L, well, we just found L. It's this, mu naught N squared A over L, times I squared? Well, we found what I was a little while ago. It's BL over mu naught N, and all of that is squared. And what you find, of course, is that a number of these terms cancel. There's an N squared here and there's an N squared here. There's an L here, which cancels an L squared, one of the L's in the L squared. There's a mu naught here and there's a mu naught there. And when they've all gone, what you're actually left with is a half B squared over mu 0. Sorry, that mu naught there was squared, of course, so you only lost one of them, times AL. But AL, that's the cross-sectional area times the length of the solenoid, is the volume of the solenoid. So once again, we've got that the energy per unit volume of the solenoid, which we will now call UB, representing the energy stored in the magnetic field, is a half B squared over mu 0. And that also will be measured in joules, which is energy per meter cubed. Now, from the first video we did in this series, What is Light, we established that the magnitude of the magnetic field in electromagnetic radiation is equal to the magnitude of the electric field divided by c, the velocity of light. So now we can take the term we just established for the energy in the magnetic field, which is a half B squared over mu naught, and for B we can now write E over C. So now UB, which is the energy per unit volume in the magnetic field, which of course is here, this term here, we just substitute for B E over C. We're going to get E squared over 2 mu naught C squared. I've just substituted that C squared, well, now I'm going to substitute C squared is 1 over epsilon naught mu naught. That we also established in the video on what is light. So if we replace this term C squared by 1 over epsilon naught mu naught, we're now going to get that the energy per unit volume in the magnetic field is going to be E squared epsilon naught mu naught divided by 2 mu naught. And of course the mu naughts now are going to cancel, and now we get that the energy stored in the per unit volume in the magnetic field is 1/2 epsilon 0 E squared joules per meter cubed. And that is exactly the same as what we just established a few minutes ago for the energy per unit volume in the electric field. That was also 1/2 epsilon 0 E squared joules per meter cubed. So what we've just established is that in an electromagnetic wave, or in electromagnetic radiation, the energy per unit volume in the magnetic field is exactly the same as the energy per unit volume in the electric field. So the total energy in the electromagnetic radiation, which we'll call UT, total energy per unit volume, is the magnetic plus the electric, which of course is just epsilon naught E squared joules per meter cubed. Or you could write that, knowing that E is equal to B times C. You could replace this, you can have this epsilon naught, keep one of the E's but replace the other with BC, and that's joules per meter cubed. Since we've simply taken one of the E's and called it BC, because that's what we get from here, and that gives us this term here for the total energy per unit volume in the electromagnetic wave. Now I want to think about the flow of energy through a box. So we've got electromagnetic radiation flowing through a box whose cross-sectional area at this end is 1 meter squared and whose length is 3 times 10 to the 8th meters. In other words, it will take light 1 second to travel from this end to this end. And electromagnetic radiation is passing through the box like this. So in 1 second, all the radiation that is in that box will move out, because it takes 1 second for the radiation at that end to get to that end. So in other words, all the radiation that's in the box after 1 second will have moved out. So all the energy that is contained in that box will have moved out in 1 second. What's the volume of the box? Well, the volume of the box is simply the length times the cross-sectional area. The length we can call C, 3 times 10 to the 8th meters, and the area is 1. So the volume of the box is simply C meter cubed. So the total energy in the box is going to be the energy per unit volume multiplied by the volume, which we just established was C. Well, that's going to be, from the formula we just derived, the total energy per unit volume is epsilon naught EBC. That was the total energy per unit volume. But now we have to multiply by the volume, which is C, so we get a C squared. And that will now be measured as joules per second per meter squared. It's the amount of energy flowing per second through the box per meter squared, because the cross-sectional area of the box is 1 meter squared. But just a reminder that C squared is 1 over epsilon naught mu naught. We've shown that, we've used that before in this very video. And so we can replace the C squared here, and we now get that the total energy flowing per second per meter squared is epsilon naught EB, and now instead of C squared we're going to have 1 over epsilon naught mu naught. So obviously the epsilon naught terms now cancel, and you get that the total energy per second per meter squared is EB over mu naught, and that's again measured in joules per second per meter squared. But joules per second is a measure of power, that's watts. So this now becomes watts per meter squared. And this term, which shows the power per meter squared, the power per area, is the Poynting vector, and that is given the letter S. So S is EB over mu 0 watts per meter squared. That is the Poynting vector. It's a measure of the intensity of the radiation per meter squared falling on you. Now, not quite finished yet, because we do have to remember that for electromagnetic radiation we are dealing with oscillating waves. In the video What is Light, we said that E was E naught times a sine wave. I'm going to drop the space term. There's usually a KZ term in there at the moment, but I only need the time variable for these purposes. So we're going to say that E is E naught sine omega t and B is B naught sine omega t. Remember, in an electromagnetic wave, the two waves are in phase, so when one reaches a peak, so does the other. Consequently, this term S, which is a product of E times B, S will therefore vary according not only to sine omega t, but sine omega t squared. Because it's E times B, so you've got a sine times sine term. So S, the Poynting vector, will vary according to sine squared. What then is the average value of sine squared omega t? Well, the average value of a sine squared term is 1/2 over a complete cycle, or number of cycles. Consequently, we can say that the average value of the Poynting vector now will be 1/2, which is the sine squared term, times now the maximum value of E and the maximum value of B, divided by mu 0. We got that from this term here, E times B. E times B means you get E naught times sine times B naught times sine. The average value of the sine squared will be 1/2, so you get 1/2 E naught times B naught instead of EB as the average value of the Poynting vector. And since B naught equals, let's write this down here, since B naught equals E naught over C, we've used that before, we can substitute for B naught there, and we get that the average value of the Poynting vector is now just E naught squared divided by 2 mu naught C. And that's in watts per metre squared, of course. And since this is a measure of intensity per metre squared, that gives you an indication why whenever we talk about the intensity of electromagnetic radiation, we have to look at the value of the electric field squared, because intensity is proportional to E naught squared. So the Poynting vector is a measure of the power measured in watts per metre squared, or if you like, since watts is joules per second, it is a measure of the energy per second per metre squared being conveyed by the electromagnetic radiation. Space by radiation. So how is energy contained in electric and magnetic fields? Well, let's think about an electric field first of all, and we'll start off by considering a capacitor. Capacitors are typically parallel plates of area A, or more accurately overlapping area A, a distance d between the two plates. From our video on capacitors, we established that the definition of capacitance was the amount of charge per volt. So it's the amount of charge on the capacitor determined by the voltage that is applied. We also learned that the capacitance was proportional to the area of the plate divided. Hello, today we're continuing with our series on electromagnetic radiation, looking at the Poynting vector. This series has videos on what is light, the Poynting vector, Fresnel equations, polarization, the interaction of electromagnetic waves on metals, and waveguides. The Poynting vector is a measure of intensity of electromagnetic radiation. Electric and magnetic fields have energy. Electromagnetic radiation has electric and magnetic fields, and therefore it has energy. Sunlight can warm you if you lay out in it. Indeed, if you lay out in it too long, it can burn you. That's because there's energy. And the heat that gets from you, or from the sun to you, doesn't get there by conduction or convection. It travels over 93 million miles of space. And what we do is we put a potential difference between the plates. The potential difference is V. And what will happen is that in the way that this is designed, there will be a negative charge on this plate here, and that will induce a positive charge on the plate below. And because of that, there will be an electric field between